In the last class, we were discussing about mm, frequency bands. So when we are discussing about the frequency response, so we have seen that amplifier will be having the three frequency bands. So one is the lowest low frequency band, another in the mid band frequency, and the third one is the high frequency band. So the amplifier gain will not be constant. Okay. So as you can see in the graph, you can see the amplifier gain is not constant throughout the frequency. So throughout the band of frequency, if you are going to see observe, so from 0 hertz to you can go for up to gigahertz or a megahertz also. So you can see the gain or the amplifier gain will not be constant parameter. So you can see there is some deviation in the gain, and you can see the as you increase the frequency of the input signal, so the gain is also going to increase in a linear way, and for a time being after some period of frequency the gain will become constant, as you can observe here. So after that again the gain, as you increase the signal frequency, again the gain is going to reduce. So as you can see observe in this parameter. So when we carefully look at this, so the amplifier will not be having a same constant parameter, that is amplifier gain is dependent upon the frequency. So why it is dependent on frequency? Because there are some certain cases because of which the amplifier gain will not be a constant. So the gain will be having a roll-off factor in the lower frequency, as well as if you see observe, so you can see there is a roll-off factor at the, as you see look at the as we look carefully look at the output at high frequency. So at a high frequency as well as low frequency. So if we carefully look the circuit diagram, so we can see that this is a common source amplifier, where in which we are going to have externally coupling capacitors has been included. So by including this external coupling capacitor, whenever we are going to have a multi-stage amplifier, so we are going to use this coupling capacitor, so that instead of directly connecting the previous stage output to the current stage input, as well as the current stage output to the next stage input, so we are not going to directly connect. Instead we are going to use a coupling capacitor in between. So by using the coupling capacitor, so you can able to couple the output of the previous stage to the input to the next stage. So these coupling capacitors, which will be usually large, and I have told in terms of microfarad it will be there. So with the usage of this external coupling capacitor, so these capacitance reactance will be very much higher at low frequency. So capacitive reactance is given by Xc is equal to 1 by 2 pi Fc. So F at 0, so you'll be having the coupling capacitor, so which we can see here some signal voltage can be coupled to the input side only when this capacitive reactance is very low. So if it is very high, means obviously it will be acting like an open circuit, and none of the voltage will be connected to the input side. Hence, if whenever the coupling capacitor will be frequency of the input signal is going to increase, then only this capacitive reactance is going to reduce. So when it is going to reduce, the obviously the effectively all the signal voltage will be appearing across the input side, so that you will be getting the maximum gain. So these coupling capacitors will affect the amplifier performance, that is in the lower frequency range of operation, that you can observe here. So the gain roll off at lower frequency because of these external coupling capacitors. And similarly, so when we have seen in the high frequency equivalent circuit model, so we have considered internal MOSFET capacitance, right? Internal MOSFET capacitance like the CGS as well as CGD, so which will be which we are going to consider, because these at high frequency, these each terminals will be acting like a capacitance effect, and because of the variation in the potential between the three terminals, and because of which you can observe that capacitive effect, so that has to be considered. So those capacitive effects need to be considered when you are going to operate at a high frequency range. So you can see there is a gain getting roll off at the higher frequency, because these internal MOSFET capacitance, which will be usually absent during the lower frequency range of operation, it will become active. That means it will become acting like a short circuit. That means it will become finite value when you increase the input signal frequency. So input signal frequency, that is a higher frequency for a higher frequency operation. So these internal gate capacitance CGS as well as CGD, which was infinite, which was acting like an open circuit in the lower frequency range of operation. So during this frequency of operation, so you can assume that this CGS and CGD was not present. So that means what? So it was acting like an open circuit. So that means there was no connection between gate and source as well as gate and drain terminal. So because of which the gain was maximum during the lower frequency range of operation. Whereas when you cross above higher upper cutoff frequency, you can say that this CGS as well as CGD will become the impedance of the CGS and CGID. So the capacitor reactance is going to reduce. So whenever it is going to reduce, so it is going to appear. That means it is going to have a finite amount of finite value, and it is going to cause the amplifier gain to roll off. So it is going to cause the amplifier gain to roll off at higher frequency, because of which you can see the as you increase the frequency greater than upper cutoff frequency, the gain getting roll off. So this is about in the midband frequency, all capacitance can be neglected. So why they have mentioned capacitance can be neglected? Because above cutoff, above lower cutoff frequency, you can see these external coupling capacitor will be acting as a short circuit. So there is no effect from the there is no effect from this coupling capacitor, because they are acting like a short circuit. And below upper cutoff frequency, that is during this operation, so your all internal gate capacitance will also be acting like a open circuit. So those effect will not have impact on the amplifier performance. Hence, during this period of time, so no capacitance will have impact on the amplifier gain performance. So that because of that reason, so this all the capacitance can be neglected when you are going to consider for the midband frequency. So in the midband frequency, since these capacitors effect will not be there, that is external coupling capacitor as well as the internal MOSFET gate capacitance effect will not be there. So you will be getting the maximum gain, and the gain will be constant throughout the period during this midband. So when you are talking about the midband frequency gain, so you can see, since because of the all the capacitance will not have impact, so because all the capacitance was absent, so because of that you will be getting the maximum gain. So the midband frequency will be getting maximum gain. And then, so as you increase the frequency, again this MOSFET gate capacitance will cause the gain to getting roll off. So this is about the frequency response, and the difference between the FH and FL. So it is going to consider as a bandwidth. So bandwidth of any amplifier, if they ask me, so you have to consider that the difference of FH and FL. So FH corresponds to higher cutoff frequency, upper cutoff frequency, and FL corresponds to lower cutoff frequency, or also called as a lower cutoff frequency, or what we call, so this is higher cutoff frequency, or it is also called as a lower cutoff frequency. So the difference between these two bands, that is that gives the bandwidth. So less than 3 dB, that gives the midband frequency gain, that is the upper cutoff frequency point. If I want to know, means I should get AV divided by root 2, so or 3 dB less than that of the maximum gain which you are going to get. So since we are going to have a gain in decibels, so this will be expressed in decibels. So less than 3 dB if I am going to find, then that gives the corresponding amplifier gain. So upper cutoff frequency as well as the lower cutoff frequency, so that corresponds to the we can easily find out the bandwidth of that corresponding amplifier. So bandwidth, if you know, means during this period of time, so the gain can be maximum. So that is what about the previous class which we have studied. And again we have seen in the single time constant network, so how to make a single frequency response of the circuit. So by considering an example that all the circuit inside the circuit all in the inside the single circuit. So if you consider this as a circuit for a common source amplifier, so if you consider this as a circuit, if you consider this as a circuit, so this is a circuit of a common source amplifier, means so at the input side as well as the output side, between the input and output side, so if you are going to realize the circuit to have single time constant network, means so this entire thing at the input side should be connected as a single resistance component and one capacitive reactance component. So single time constant means you should have one reactive component and another one is resistance. So here in this chapter or in this entire syllabus, we are going to consider only capacitive as well as the capacitive as a reactance which you are going to consider, and hence one resistance means a resistance component will be making it of. So this is how you are going to consider for the amplifier. So what I should do is so this whatever this circuit is there at the input side and all, so I should make them into convert into a single time constant network. So single time constant network means it should have either R and C network, or it should can have C and R network between the output and input. So between the output and input, you can have either R and C combination, or it can have C and R combination. If you are going to have R and C combination, the response will be like a low pass network response, and this C and R means it will be having high pass response, and this corresponds to the low pass network transfer function. This corresponds to the high pass network transfer function. So high pass means C and R, low pass means R and C. So this is the what is this k divided by 1 plus s by omega naught. So this k corresponds to what? So k corresponds to the amplifier gain. Okay. So that is constant gain divided by 1 plus s by omega naught. This corresponds to the transfer function for a low pass for a low pass sorry, transfer function of a low pass network type. And this is for complex frequency variable s. So if I want to know have a physical frequency, then I can substitute s. In place of s, I am going to substitute j omega, and then the modified transfer function I can have k divided by 1 plus j into omega divided by omega naught. So if I want to take the magnitude, because you are having imaginary term at the denominator, so if I want to take the magnitude, so magnitude means you can take the magnitude in the numerator as well as the denominator as a square root of 1 plus j square is minus 1, so minus 1 square, so it is become plus, so plus of omega divided by omega naught whole square. So this is about the magnitude response. So this one, along with that phase component also it will be there, so minus tan inverse of omega divided by omega naught, that gives the magnitude as well as the phase response for the angle of the given transfer function. So once transfer function has been done, then we need to check by transfer function, in the sense it is nothing but an amplifier transmission gain. So if I want to find out the transmission gain, so I should consider two conditions. So that is when omega is equal to 0, when omega is equal to omega naught, and the omega is equal to infinity. So three cases I am going to take, but here they have given only two cases. So either you can take another case as well. So when omega is equal to 0, if you substitute or in the so if you substitute so if you substitute over there, so wait a minute. So if you substitute the omega value, that is equal to 0 in this equation, corresponding equation, so what you will be getting, 0 by anything, it is nothing but a 0. So whole denominator term, it will be equal to 0 plus 1. So square root of 1 is 1. So you will be getting the maximum value when omega is equal to 0 is nothing but the transmission gain k. So this will be the constant, that is numerator value you will be getting. And when omega is equal to infinity, so substitute omega is nothing but a test frequency. Omega is equal to infinity if I am going to substitute. So infinity by omega naught, so this is finite amount of value. So this entire term, so this entire denominator term, it will be equal to infinity, infinity plus 1. So it is negligible. So infinity, square root of infinity means it is going to have a very high value. So anything divided by infinity, so you're going to have a value of 0. So this is the transmission of frequency at omega is equal to infinity. You will be having the transfer function as a transfer function as of low pass type. So you'll be having 0 as the output when the transmission of frequency at omega is equal to infinity. So now the same analysis can be done for the C and R. So this is a C and R network. Suppose it is also a single time constant network. So it is arranged in the form of C and R. So that is nothing but a high frequency, high pass type. So this is nothing but a high pass type. This is nothing but a low pass type. So this is high pass type means, so you can assume that as it is a made up of a single time constant comprising of C and R between the output voltage and input voltage. So we can have the transfer function for the high pass type as this one. So this is a transfer function using complex frequency variable they have written. So now if I am going to write in terms of physical frequency, we need to substitute in place of s as j omega. So j omega, so j omega means you can substitute the value for the omega. So you can substitute the value for omega, so starting from 0 to infinity. So if I am going to have this equation, so you will be getting this as a transfer function for physical frequencies. And taking the magnitude, so you will be getting the magnitude k bar, so by square root of 1 plus omega naught by omega whole square. So you will be having this value. So that is the magnitude response. And then so this is the response of the magnitude response of this transfer function. And if I want to have a phase response, so this phase response is given by tan inverse of omega naught by omega. So this is going to have this equation. So now if we find when the frequency is 0. So what will happen? So for this transfer function, when frequency is equal to 0, so here we are going to have a frequency is equal to 0. So anything divided by 0, that is infinity. So denominator term will be having infinity. So you'll be having 0 as the output transmission gain. And when omega is equal to infinity, so omega is equal to infinity, anything divided by infinity is nothing but 0. So 1 plus 0, so square root of 1 is 1. So you'll be having the value of the transmission gain is k. So this is how you are going to find. So 3 dB frequency, how where you have to find. So for a given single time constant network, so if you have realized with one R and C component or C and R component, so that we can find the 3 dB frequency at 3 dB frequency will be equal to 1 over R into C or C into R. So that gives the 3 dB frequency for any single time constant network. So it is having one reactive component and one resistive component. So this is what for the 3 dB frequency plot. So this we have studied in the previous class. Now we will look for the today's class, where in which you can see the frequency response of high frequency response of an common source amplifier. So in order to understand this high frequency response of the common source, before I start with the high frequency response, you should know what you mean by high frequency response. So high frequency response something like you should analyze this figure. Okay, so this is a circuit diagram. So this is the common source amplifier. So this is a common source amplifier, you should remember, because the source is connected common between the input and output. So input is applied to the gate and output is applied, we are going to take at the drain terminal. So this is the resistance, drain resistance. So this is the coupling capacitor CC2, CC1 is the input side coupling capacitor, and this is the signal source voltage along with the signal source resistance associated to the input side of the gate. And this is the input resistance. It will be in terms of mega ohm, because the input resistance of a common source is very high. So RG is very high value. And this is a bypass capacitance, and this is the output coupling capacitor CC2 from the output of the drain terminal through the coupling capacitor. We are going to connect to the load. So RL is corresponds to load. So this remember, you should remember this is the circuit diagram of the common source amplifier. So for this common source, if I am going to check for the high frequency, so for the same, in the next topic when I am going to discuss, I am going to discuss about the low frequency response of the common source amplifier. Today I am speaking about high frequency response of common source amplifier. Tomorrow I will be discussing about low frequency response of the common source amplifier. For both the diagram, for both the analysis, so we are going to have we have to take this as a common circuit diagram. So this is a common source amplifier with all the capacitance will be included within this. So now, if we since I am going to talk about the high frequency model, so high frequency response of the amplifier. So this is the general frequency response of any amplifier. Okay, this is general response of any frequency response of any amplifier. So if I am going to talk about common source amplifier, then if I high frequency, if I am going to consider, so this is nothing but a high frequency response. So for this high frequency response, we have already developed a high frequency equivalent model, right? So we know what to be included in the high frequency model, and also we know that since in this circuit diagram, so there are various coupling capacitors are there, right? So bypass capacitor, input coupling capacitor, output coupling capacitor, as well as a bypass capacitor. So three capacitors are included in the common source amplifier. So when I am going to consider for a high frequency response of common source amplifier, so during this, you can see that during this low frequency operation, so during this the external coupling capacitor will not have any impact, right? So when I am going to talk, or when I am going to analyze the behavior of the common source at high frequency band, so all these coupling capacitors, input side coupling capacitor, output coupling capacitor, as well as the bypass capacitance, all the three coupling capacitors will be acting as a short circuit, correct? So because these capacitors will not have any impact at the high frequency response, because in the high frequency response, so these coupling capacitors will be usually absent. So usually absent andre ಏನು ಆಗಬೇಕು high frequency response ಅಲ್ಲಿ, so I can consider this as a short circuit. So from the R signal, if I am going to have a short between the gate and input gate resistance, so this is I can remove this coupling capacitor CC1, CC2, as well as CES, or you can consider this as being shorted. So shorted andre, so it is having a zero impedance, so that it is acting like a short circuit. Okay, So that thing you should remember. So what type of analysis we are discussing? So high frequency response. So during high frequency response, external coupling capacitor will be considered as a short circuit. So these will be not included, or it will be not taken into consideration when I am going to deal with the high frequency response. Okay. So by doing that, only we are going to consider CGS as well as CGD. So now consider the high frequency response equivalent circuit. So side by side I will just show the circuit diagram as well as the this is the circuit diagram. So what is there? This is shorted. So this I should remove. So at the input side, what is that? This is the input side component is there, excluding CC1. So V signal, R signal as well as RG is there. So if you look at this circuit diagram, so the high frequency equivalent circuit model, so you'll be having V signal, R signal as well as RG is there. So same side. So you can see this is also there. So same input side as well as input side here also it is there. So what is there in the output side? So output side means we are going to have to look from the output voltage terminal. So when it is when we are going to analyze the high frequency equivalent circuit model, so this will be shorted to ground. So RD is there, RL is there. So this is a common point. So output voltage point, and between drain and source, you are going to have a finite amount of resistance R0 will be there. So R0, RD as well as RL will be the resistance which will be connected with between the output and ground. So this coupling capacitor will be shorted. So this will be not having an impact at the high frequency. So I am going to short it, and I am going to have a three resistance are will be there. So the same thing you can see over here. So at the output side you can see RD as well as RL. Okay. So forget for a time being finite amount of resistance. So this is the when we look from the output terminal, drain terminal, RD as well as RL resistance for which output voltage will be appearing. So now if you look at this, if you look at the circuit diagram again, so this is nothing but connected to ground, and this is also shorted. So I can replace this MOSFET, common source MOSFET into corresponding high frequency equivalent circuit now, because input side is over, output side is also over. Now only left out is how I am going to represent the common source MOSFET. So this for this common source MOSFET I can replace with its corresponding MOSFET can be replaced with its corresponding high high frequency equivalent circuit model. So CGS will be there, CGD will be there, and the constant current GM into VGS will be flowing between drain and source, since it is a common source amplifier. So it is going to current will be flowing between drain and source. So it is going to have a GM into VGS. And if I am going to consider the channel length modulation effect, so you can have R0 is a finite amount of resistance that is going to be connected, or we are going to consider that effect R0 between drain and source. So between drain and source, I'm going to include finite amount of resistance or not. So this is nothing but a MOSFET high frequency equivalent circuit, and this is the output resistance, and this is nothing but a input resistance which has been connected. So this completes about the circuit for the circuit diagram for common source amplifier corresponding high frequency equivalent circuit. So now what we need to do? So we need to convert this entire network into corresponding single time constant network. So if I'm going to find out in order to find out the analysis of an frequency response of a common source amplifier, I need to make into corresponding single time constant network. So I should make it as a single time constant, so that it can have R and C or C and R, because in this topic we are going to have only reactive component, which will be have a capacitance, and resistance component as a other finite resistance. So I need resistor as well as a capacitance. So now I need to make into single time constant. So before that I can see what is the output voltage. So what is the output voltage? So first we need to find out what is the output voltage. So since we can see output voltage is appearing between drain and source, that is having what the current flowing between the drain and source is what? So between drain and source, the current flowing is GM into VGS. So that is a constant current that is flowing. And after that, I can see what is the resistance it is going to have between the output voltage node. So that is R0 parallel with RD parallel with RL. So these are the three resistance that is the equivalent resistance equivalent to R0 parallel RD parallel RL. Whatever the value you are going to get. So if I am going to find out, if I want to find the 3 dB frequency, if I want to find the output voltage, so multiply current with the resistance, so you will be getting the value of the output voltage. So output voltage will be equal to minus gm into so this parallel equivalent of RD, RL as well as R0, I can write it as RL dash, and the current which is flowing here is GM into VGS. So GM into VGS into RL dash I am going to get. Okay, so this is the corresponding output voltage. So now, so if we look at this gate capacitance like CGS as well as CGD, if you look at the CGS value, so CGS value it is nothing but gate to source capacitance value. So this gate to source capacitance value has been connected across the input side. So between gate and source, so this is nothing but the input side. Whereas what is the value of the capacitance CGD? CGD is connected between the gate and drain. So if I want to consider this to be considered into the effect of the input side, so what I need to do? So because since gate to drain capacitance is going to connect to the input node G and output node D. So when I am going to have this type of network, so it is called as the Miller effect. So Miller capacitance. Okay. So this gate to drain capacitance is also called as a Miller capacitance because it is Miller capacitance because this is going to connect between the input and output terminal. So our input terminal is gate terminal and output terminal is the limited drain terminal. So it is going to act like a feedback path. So since it is going to act like a feedback path, so we cannot directly take this CGD as connected to only with respect to input, or we cannot consider this as a complete as a output because the current will be flowing between the gate and the drain as well as the drain and the gate. So in order to do that, so what we should do is the current which is flowing between the gate and drain we need to find out. So when we develop such a way that if I am going to find out the value of IGD, then I can make the this gate and drain capacitance to be connected between gate and source. So by using equivalent circuit by equivalent capacitance value CG. So whether you people are understanding or what? So this is the output voltage. So output voltage is nothing but what? Current multiplied with the resistance. So resistance is nothing but RL dash. So RL dash is nothing but R0 RD RL parallel. So RL dash into GM into VGS. So this is the output voltage expression. So now if I want to find the value of the input current at the input current that is flowing between the gate and drain. So this is the IGD is the current that is flowing between the gate and the drain. So now if I want to see what is the amount of current that is flowing, so IGD. So the IGD is the current that is flowing between the gate and drain. So now we need to find out the value of the IGD. So if I find the value of IGD, then I can replace, I can remove this CGD, that is the gate and drain. I can remove and I can connect an equivalent capacitance which is going to draw an equal amount of current without changing any terminal voltage or current value. So what I am going to do, so since CGD, so CGD is the capacitance that is going to connect between the gate and drain. So this equivalent resistance I am going to find out. So that equivalent resistance I am going to name it as a C equivalent. So this C equivalent will be equal to the CGD. So C equivalent will be equal to what? So we need to find that such a way that the C in should be equal to the same amount it is drawing when it is not connected like that in the before. So ಇದಕ್ಕೆ ಇವಾಗ ಹೆಂಗೆ equivalent capacitance which is going to connect between gate and ground, and if I want to consider it the output side means drain and gate are going to have another output as well, but since it is not required, so you can say that so between the gate and drain, if I'm going to add one raise one capacitance means you should carefully listen. So it has to be connected such a way that the current drawing by the equivalent capacitance must be equal to that of the current that is flowing between the gate and drain. So that if I am going to obtain, then we can easily convert into a single time RC constant. So now we have to scratch a little bit. So if I am going to talk about the high frequency response, so in this frequency response I can show. So this is the frequency response. So in this frequency response, in the vicinity of upper cutoff frequency, because you have to recall we are dealing with only higher cutoff frequency. So whenever the input signal is at higher frequency, so try to see at the during the in the vicinity of the upper cutoff frequency, and in the vicinity of the upper cutoff frequency means in the near to the upper cutoff frequency, you can see the current flowing or the effect of CGS and CGD will be less. Because of this, the current since the CGS and CGD will be having high impedance, so the current flowing inside the CGD will be less. So because of this, we can say that during the upper cutoff frequency, in the vicinity of upper cutoff frequency, current flowing will be negligible. And if I consider the circuit as well, so the current flowing will be negligible, and the current is only due to the GM into VGS. Okay, so current is only due to, so if you consider so the figure, so here the current is only due to GM into VGS. So this IGD is very small when compared to the current GM into VGS. So we're going to neglect this gate to drain capacitance. Okay, so now we can see this is the frequency response of the common source amplifier. So here you can see uh, the gain will be constant. So we are not interested in the lower frequency range of operation. We are interested only in the upper cutoff frequency range of operation. So higher in the lower frequency, the gain will be constant, and as you increase the frequency, the gain getting roll off. So this is the frequency response of common source amplifier gain. So now we need to find out what is the equivalent output resistance. So output side lane is a RD parallel, RL parallel, R naught. So we are going to get we are going to name it as a RL dash, R naught parallel, RD parallel, RL. So now we know that what is the gain from gate to drain. So gate to drain yesterday andre, so we know that it is nothing but equal to minus GM into RL dash. So it minus GM into R naught parallel RD parallel RL. So that is nothing but the gain which you are going to get. So we are going to get the gain across drain to source because the source is already grounded. So we are going to get the output voltage across the drain to source terminal. So VDS will be equal to V naught when it will be equal to minus GM into RL dash. So now what is the current that is flowing between the gate and drain? So that is the IGD. So IGD will be equal to what? So IGD, if I want to find IGD means so current will be flowing. IGD will be equal to VGS minus V naught. So why VGS? Because the gate and ground, that is shorted, hence we can say that VGS minus of minus GM into RL dash. Okay, and I can write that as a figure. So IGD can be written as the capacitance multiplied with VGS minus V naught. So VGS is the voltage across this point. So this is the voltage across this point. So we have to find out the VGS. So it should be equal to V signal into RG divided by RG plus R signal into CGS divided by total resistance. Okay, so like that you are going to find out the value. So S into CGD into VGS minus V naught. So minus V naught is there. So V naught already we have found out the expression which will be equal to what? So V naught will be equal to GM into VGS into R naught RL dash. So GM into RL dash. So we are going to substitute the same value over here. So VGS minus V naught. So minus GM into RL dash. So that is the same equation. So in that I am going to take the common as a VGS term. So IGD SGD into VGS common term 1 plus GM into RL dash into VGS. So this is going to be useful in the relation. So when you are going to solve the problem, so what is the IGD if I want to know for common source amplifier? So you will be having the S into CGD VGS minus V naught. So V naught is nothing but a minus of minus GM into RL dash. So that value you are going to substitute and you will be getting the value of the current expression. So the IGD value is nothing but S into CGD into 1 plus GM into RL dash into VGS. So this is the current. So now if I want to see the circuit at which has been partitioned there earlier. So this is the limit of partition. So XX dash ಅಂತ partition ಮಾಡಿಬಿಟ್ಟಿದ್ದೀವಿ. So if we are going to have one side of the path will be one side of the circuit will be what we tell one side of the IGD we have found out. So now next we have to find out what is the XX dash from existence from the gate to drain. So gate to drain ಇದ್ದಾಗ ಏನಾಗಿದೆ? So we are going to equate the value of the current S into CGS into VGS which will be equal to S into CGD into 1 plus GM into RL dash. So this is an equivalent capacitance value. So you should remember C equivalent. So this is a C equivalent when you are going to draw C equivalent. So when you are going to have a capacitance which is going to connect between the gate and drain, so you have to monitor for the corresponding equivalent capacitance value multiply with you should have provided that it should have the same current. So when then only I can make it a corresponding circuit into corresponding gate to source problem. So I can say that so this is the current is there. So now I am going to find out the current after finding the current. So what is the output? So that is the C equivalent into VGS. So this C equivalent into VGS is the voltage drop across the capacitance newly added capacitance between gate and ground. So newly why we are adding the gate and ground because CGD cannot be considered as an input capacitance or output capacitance since it is associated at the input side as well as output side. So this is nothing but the Miller effect. So it is also called as a Miller capacitance. So in order to calculate for the Miller capacitance, so Miller capacitance can be calculated by connecting the by connecting one equivalent capacitance. So we are going to find out this by connecting one equivalent capacitance. So which is going to draw the equivalent amount of current IGD. So IGD ಎಷ್ಟು ಕಂಡುಹಿಡಿದಿದ್ವಲ್ಲ, so say the same value of the current it must flow in the newly added capacitance C equivalent. So that C equivalent value will be equal to what? CGD. So this is CGD into 1 plus GM into RL dash. So that is what value that you are going to have the for the C equivalent. So C equivalent should be equal to CGD into 1 plus GM into RL dash. So SGS gets cancelled. C equivalent will be there. So VGS will get cancelled. So you will be getting the gain. So for a capacitance value, so you are going to find the capacitance value C equivalent as CGD into 1 plus GM into RL dash. So now we need to find out what is the input voltage. So in order to find out the output voltage, so we first convert the input voltage VGS into corresponding in terms of the signal voltage, and then later I can substitute in the gain expression. Okay. So VGS will be equal to what? So by looking at the figure, VGS will be so the value of the VGS, so VGS circuit will be there. So I have to recall about the circuit. So you can see in this circuit. So VGS, so this is the voltage across this point. So VGS will be equal to what? V signal into RG divided by R signal plus RG into 1 divided by 1 plus S by omega naught. So that is the transfer function. Along with that, you can see this is the expression. So now we can easily find out the value of the high frequency response. So VGS. So VGS will be equal to V signal into RG divided by RG plus R signal plus into 1 plus 1 divided by 1 plus S by omega naught. So this is why because so we can see the circuit relation will be taking place with respect to R and C combination. So we can see this is a C equivalent capacitance and this is a CGS. So since it is a connected in parallel, so you'll be having C1 plus C2 as the capacitance effect. Is it clear? So this is about the capacitance effect. So that is a total. It will be equal to C equivalent. So this C equivalent will be equal to CGS plus CGS plus CGD into 1 plus GM into RL dash. So that is what the current. That is what the C equivalent capacitance. So once you find the C equivalent capacitance, now what we need to find out? So we need to find out what is the equivalent circuit at the input side of the voltage as well as output side of the voltage, so that we can write a single time constant network. So single time constant network. So there from that we are going to find out the value of the V signal as well as the omega naught corresponds to the upper dB frequency. So this upper cutoff frequency omega naught will be equal to 1 by C into R signal dash. So why that is the limit of one time signal time constant. So it will be equal to um, the value of the one time signal constant will be equal to. So here you can see this is the R signal dash which will be equal to RG into R signal divided by R signal plus RG. So it will be nearly equal to the R signal value. So this is one resistance component is there. So here two capacitor component is there. So when we want to have a two parallel capacitors, so that will be equal to C in will be equal to C equivalent C equivalent will be equal to CGS plus C equivalent value. So that is what you are going to get over here. So C equivalent will be equal to CGD multiplied with 1 plus GM into R and dash, as well as if I want to constrain into single STC network, so you're going to have V signal as the output. So V signal into RJ divided by RJ plus R signal into 1 by 1 plus S by omega naught. So this is the transfer function of the amplifier transfer function, and this is the this is the input signal voltage VGS. So now VGS has been modified. Now we can easily calculate the value at STC network the corner frequency. So here we have denoted in general what is the 3 dB frequency omega naught. This is because the configuration is of a low pass type. Since it is a low pass type, we are going to have a transfer function like this. So that 1 divided by 1 plus S by omega naught. So omega by omega naught. So now if I want to find out the 3 dB frequency, omega naught will be equal to 1 by R into C in. So R signal dash into C in, that gives the value of the 3 dB frequency. Once the 3 dB frequency has been done, so C1 will be equal to C2 will be equal to C in will be equal to CGS plus C equivalent. So C input capacitance. So what is C in? ಇಲ್ಲಿ ನೋಡಿದಾಗ ಏನಾಗುತ್ತೆ? So C in will be equal to, so addition of these two. So C in will be equal to CGS plus C equivalent. So C equivalent is given as CGD into 1 plus GM into R L dash. So that value is going to substitute over here. C in will be equal to CGS plus C equivalent. So CGS plus CGD into 1 plus GM into R dash. So this is about the value of the capacitance C in. So C in value ಕಂಡುಹಿಡಿದಾಯಿತು. Along with that resistance value also we have found out at the input side. Now we can able to find out the following expression for the high frequency. High frequency ಹೆಂಗೆ ಕಂಡುಹಿಡಿತೀರಾ ಅಂದರೆ, so again go back to the high frequency response. So that is the output of the amplifier. So V naught output voltage, so V naught will be equal to what? Minus GM into RL dash into VGS is there. So that is a given expression. So minus GM into RL dash, if I am substituting, so minus GM only correct ಇದೆ. Whereas minus GM into RL dash you can see. So first note down the output voltage expression. V naught will be equal to minus into GM into RL dash, followed by VGS is there. So VGS can be written as what? So this is the example for the VGS input voltage. So this example I can substitute over here. So when I substitute the value of the when I substitute the value of the VGS, G minus GM into R dash into V signal VGS, so you will be getting this as a value. So once this equation, so everything is done, so next is V naught by V signal. So here whatever the V signal is there, so V signal where it is, so this is multiplying with another VGS, V signal will be there, so that V signal will be coming to the denominator, and hence this will give the 3 dB frequency gain response. So 3 dB frequency in this minus GM into RL dash into RG divided by RG plus R signal dash will be equal to AM, midband frequency gain, or it is also called as the gain of the common source amplifier, AM. So entire thing is constant for a given value. So divided by 1 plus S by omega naught. So 1 plus S by omega naught. So S in place of S, I can 1 by S by S omega naught. So I can substitute the value of the omega naught will be equal to 1 by R into C. So R in into C in into R signal dash I am going to substitute, so that I am going to get the upper 3 dB frequency. So once I find the upper 3 dB frequency, so easily I can find out the frequency range of operation. So F is value will be equal to 1 by 2 pi into R into C. So this is how we are going to find out the response for the upper 3 dB frequency or higher frequency of the common source amplifier. So any doubt is there? So any doubt means you should analyze this circuit. So this is the circuit, and this is what you are going to have doubt. So why I am going to consider this. So this is because so this is a Miller effect. So because it is a Miller effect, because it is going to connect between the input side as well as output side, so I cannot directly take. So I should take by considering it. It should have all the terminal current and voltage must be same. So for that I am going to rename the CGD as equivalent to C equivalent, C equivalent resistance. So it is going to connect between the gate and ground. So only thing is that this CG or the this CGD C equal whatever it is there. So CGD can be written in terms of C equal. So that is going to draw the same equivalent current, that is IGD. So IGD value ಕಂಡುಹಿಡಿಯಬೇಕು. So V naught value is nothing but minus into GM into RL dash into VJ. And if I find out the value of the C equivalent value, so obviously I can find out the value of the single time constant network by considering so one resistance component and one capacitive component like this, and I'm going to have the um, single time constant network. So after that I'm going to substitute the value of the minus gm into r in place of vgs. I'm going to substitute the value of what is vgs. So vgs will be equal to what? So v rg divided by rg plus r signal into s into cgd. So that is what we are going to find out the high frequency response. So this is how the frequency response of the common source amplifier. So first we calculate the value of gate to drain capacitance, the gate to drain current, and it is very small when compared to GM into VGS. So because it is small, I am going to because since it is a small value of the capacitance, and this value will be connected between the input and output. So the value of the current at the vicinity of high frequency is very small. So GM into VGS. So input voltage which we have obtained over here is only because of the GM into VGS, not with respect to IGD. So because near the vicinity, so the current component because of output voltage is only determined by this current multiplied with this resistance. So we will be having this as a minus GM into RL dash into VGS. So this VGS will be the output voltage. So now when we consider the effect, so this we are going to have a CGD will be replaced by its corresponding equivalent capacitance, which is going to draw the same amount of current. So what is the how much the current I will be equal to? So where the current is flowing IGD, IGD is flowing between what? So between the gate node as well as the drain node. So between the gate node and drain node. So what is the voltage across the gate node? Voltage across the gate node is VGS. And what is the voltage across the node voltage across the V node? So it is nothing but the output voltage V node. So the current IGD will be equal to, so this voltage minus this voltage, right? So IGD will be equal to VGS minus V naught into corresponding capacitance which is flowing, that is S into CGD. S into CGD, the same thing which I have written over here. S into CGD multiply with the node VGS minus V naught. So I substitute the value of V naught as minus GM into R dash into VGS, and find out the expression for the gate to drain current. So gate to drain current will be having this expression. So now after finding the value of the current, so I can now connect the capacitance CGD into corresponding C equivalent value by connecting to the gate and the node, and then I can substitute which will be equal to, so C equivalent into VGS, which is going to be equal to S into CGD. This is the IGD value. So this value is going to consider, and I can find the value of the C equivalent value. The C equivalent value ಕಂಡುಹಿಡಿದಾದ್ಮೇಲೆ, so next thing is that I should know what is the input gate to source voltage. So I am going to find out the gate to source voltage for a single time constant network. So we will be having the this is the value. So V signal VGS will be equal to V signal into R naught divided by R1 plus R naught. So V signal into RG divided by RG plus R signal. So this is nothing but input voltage VGS into 1 over 1 plus S by omega naught. So this is nothing but low pass frequency type, because if we look at the single time constant network, if I am going to consider, so we'll be having one R resistance component and two capacitance. So I can make it into single capacitor component. If I make a single capacitor component means yeah, I will be having R and C combination, which is of low frequency type. And since it is of low frequency type, R and C, so R signal, so low pass type, sorry, low frequency, low pass type network. So you will be having um, the response, that is the transfer function as this one. So 1 by 1 plus S by omega, and if you substitute the value of break frequency or corner frequency if I want to find, so substitute the value of R and C value, so you'll be getting this as the 3 dB frequency. So whether people are understanding or what? Hello? Hello, students.
Yes, sir.
Jason Varghese.
Yes, sir.
ಕಂಟ್ರೋಲ್ ಸಿಸ್ಟಮ್ಸ್ ಅಲ್ಲಿ ಮಿಲ್ಲರ್ ಕೆಪಾಸಿಟೆನ್ಸ್ ಮಿಲ್ಲರ್ ಎಫೆಕ್ಟ್ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡಿದಾರಾ?
No, sir.
Still they have not done, na? So Miller effect, Miller capacitance and all feedback ಮಾಡಿರ್ಬೇಕಲ್ವಾ, ನೆಗೆಟಿವ್ ಫೀಡ್ಬ್ಯಾಕ್ ಸ್ಟಾರ್ಟ್ ಮಾಡಿರ್ಬೇಕಲ್ವಾ?
Feedback ಆಗಿದೆ, sir.
Feedback ಆಗಿದೆ. So they will be doing. So what is Miller effect? Even I will also do in the next chapter. So before that, since gate and drain we are going to have a capacitance, so it is going to be connected between the input and output. So the capacitance cannot be considered as the input side as well as the output side. So for that, whenever we are going to have a feedback like that between the input and output, so we are going to consider that effect as a Miller effect or Miller multiplier. Okay. So for that, you are going to consider the current has to be same like this. Okay, so if I want to, I cannot directly consider this equivalent resistance as this one, because if I want to modify, if I want to modify between the gate and drain, this capacitance is there. So that gate and drain capacitance remove ಮಾಡ್ಬಿಟ್ಟು, if I'm going to consider at the input side means, so I should provide that the current flowing in the new capacitance which I'm giving, that is the C equivalent capacitance ಅಂತ, so that should be same. So then only I can connect like this, provided that the current, voltage, everything it is going to be remain same. So C equivalent value is nothing but C equivalent, so that is the current flowing is we need to find out, and finally I can find out the response, frequency response of the common source amplifier like this. So this is about the common source amplifier. So this is the midband frequency gain, we will be having the maximum gain, and after that 3 less than 3 dB you can see the upper cutoff frequency which will be equal to omega h, which will be equal to 1 by 2 pi fh will be equal to 1 by 2 pi into r signal dash into C in. C in will be equal to what? C in will be equal to, so C in will be the input side of the capacitance, that will be equal to CGS plus C equivalent. So that is since these two are being connected in parallel, so equivalent capacitance we are going to consider as C in, and equivalent resistance at the input side is nothing but what? So equivalent resistance is R signal dash. One R signal dash is there, and these two I am going to make it as a single capacitance, that is equal to C in. C in will be equal to CGS plus C equivalent. So C equivalent is this one plus CGS, that gives the one single time constant. So this is going to have a one single capacitive component, and this will be the one resistance component. So through that I can obtain the value of the single time constant ಮಾಡ್ಬಿಟ್ಟು, so I am going to obtain the gain expression, and I am going to get the 3 dB frequency part as well as the frequency of the input signal fh. Okay, so with this I will just conclude today's session. So tomorrow I will just explain once again so that people will understand. Okay, I just conclude today's session. Okay, bye. So we'll meet you tomorrow. So that is only one topic is there. So that is the low frequency response, and another one single topic I will left out. So that I will just conclude with tomorrow.